Okay, this will be the counting sort, by the way. And for the counting sort, this is definitely a non-comparison based sorting algorithm. Whereas it is particularly efficient when the range of input values is small actually compared to the number of elements to be sorted. This is actually basic because you will just count here. It is an integer sorting that sorts element based on their frequency or count. It works by determining the range of the elements, counting how many times each element appears, and then using that information to place the elements in the correct order. So for this one right now, you will be going to determine the range. That will be the step. Then create a count array, populate the count array. So compute the cumulative count and build the sorted array. So there will be 5 steps only. That is basic for you actually. Now, determine the range, find the maximum, minimum values in the array. So what will be the maximum, what will be the minimum values, and write that and pertains to that. Then creating a count array. So that's the time that you will create an array where the index represents the element in the input array, and the value that index represents the count of occurrences of that element. And afterwards, you have to populate the count array, iterate through the input array, and increment the count of each element in the count array. Then compute the cumulative count, then modify the count array by updating each element to store the cumulative sum of the previous counts. And that step helps you to determine the correct position of each element in the sorted array. So for this one right now, actually building the sorted array, traverse the input array, place each element in the correct position, then using cumulative count array and decrement the count for each element. So you will begin to decrement that actually -1. So after you will begin to certainly check everything. Time complexity will be O n plus k. So when we say n, that is referring to the number of elements in the input array, and the k, the range of that is talking to the range of your input values, the difference between the maximum and the minimum values of that input array. So the first step is you have to, since the first step there, to count the number of occurrences of each element, which takes linear time. So build the cumulative count. The next step involves updating the count array to solve the cumulative counts of element. That will takes the linear of, I mean the O of k time. So placing elements in sorted order, it will finally place each element in correct position in the input array. So that step will also takes linear time. So that's why our the overall time complexity in counting sort is definitely, for the best, average, and worst case complexity is definitely 0 n plus k, where if k is not too large compared to your n, counting sort can be very efficient actually. So counting sort will always process all n elements and the inner range of elements k, whether they are spread out or not. Hence, the time complexity does not change between best, average, and worst cases. So for this one right now, for the space complexity, for that is still the same thing, O1 plus k. This remains the same across all cases as it depends on the um, number of elements and the range of input k. So meaning here then, the count array to store the frequency of each element, which has the size of the same thing of k. Then the output array that holds the assorted element, which has the size of linear time. That's why definitely this is linear of n plus your k, which is the range of the input values. So that's the counting sort, by the way, and I'll begin to also illustrate that in the other